Hello everyone, welcome to the 11th video of our lecture series. So in this video we are going to talk about quantum harmonic oscillator. This harmonic oscillator, this is really important in all in classical physics also and quantum physics also. So why this? So harmonic oscillator potential. So in one dimensional, it can be expressed as half kx square. So where k is what? So k is spring constant. So let us understand this first. So suppose we have a spring attached to a wall. So let us understand first this classically what this how this potential is coming. So suppose we have a spring along which and a mass is hanging. So suppose we have a mass m and we have a spring and its spring constant is k. So this spring constant, it will depend on the properties of the spring and its physical properties basically. So suppose we displace this. So this is our equilibrium position, suppose. So this is x0 and the system is at rest. Now suppose we pull this mass by a length x. So this is x. So what will happen? So there will be a restoring force. So what is restoring force? So if we pull this mass by a value m, by a value x, then there will be a force acting to the opposite of this displacement, which will try to bring back the mass to its equilibrium position. And what will be the value of this force? So it will be minus kx. So why minus? Because it is acting on the opposite direction of our stretching. And similarly, if we compress this in this direction, so there will be a restoring force in this direction. So this restoring force will always try to bring back this mass in its original position. So that is why there is a negative sign, because our displacement and the force acting on the body, they are in opposite direction. So if our force has this form, so what will be the potential? We know that force can be expressed as the negative gradient of potential. That is a standard result, and we all know. So in one dimension, we can write this force to be minus del v del x. So this is our minus kx. So if we do the integration from here, we have the functional form of derivative of the potential to be half kx square. So from here in classical physics, so the potential is quadratic in length. So similarly in quantum harmonic oscillator, we have a potential which is of the form of half kx square. So now why this potential is so important? So suppose we have a generic arbitrary potential. So this is our v and this is our x, and suppose that this point x0, so this is our equilibrium position. So around this equilibrium position, we can express this potential in Taylor expansion form. So what will be this? So v of x0 plus x minus x0 del v del x at x equal to x0 and so on. So this is our function of the potential. If we express this around this x0 for small displacement. So now if x0, this is an equilibrium point or equilibrium position, then what we will have? Then we have del v del x at x equal to x0, it must be 0, because for equilibrium position there is no force acting on the system, and we have this term to be 0. So, and now this v of x0, it is a reference point, so we can take this to be 0, because it is just adding a constant value, and since we are interested in force, so we are taking derivative, so derivative of a constant value is 0, so that is why we can assume this to be 0 for simplicity. So now how can we express v? So vx can be expressed as half x minus x0 squared del 2v del x square at x equal to x0. So if we compare this with this equation, so here basically x means displacement, that means x minus x0, so x minus x0 should be there, so force is minus kx, x minus x0, and derivative, and we have potential to be k x minus x0 squared. So now if we assume if x0 is 0 point, that means origin is our equilibrium, or we consider our equilibrium point at origin, then we will have this potential of this form, half del 2v del x square at x equal to 0 and x square. So this we can treat this as our spring constant. So we can write, if we write this as k, then we have our potential to be half kx square, where x is what? X is displacement with respect to our equilibrium position, with respect to our equilibrium position. So that is why it is too much important to study this harmonic oscillator in classical physics and quantum physics, because if we have any general kind of potential and we know our equilibrium point, then around that equilibrium point we can always consider our potential to be a harmonic oscillator kind of potential. For larger displacement this is not true, because this Taylor expansion is this is valid for very small region only. So around that equilibrium position we can always consider our physics from the viewpoint of our harmonic oscillator treatment. So that is why it is very much important and necessary to study this harmonic oscillator in classical domain and quantum domain. So with that idea, so let us now proceed with our quantum harmonic oscillator. So the quantum harmonic oscillator Hamiltonian, it can be written as, we have our kinetic energy term plus we have our potential energy term, so it is half k x squared. So and also we know that for a harmonic oscillator, classical harmonic oscillator, natural frequency of oscillation, it can be represented as k by m. So where k is the spring constant and m is the mass of the body, so we can write k as m omega square. So if we replace that, we have our Hamiltonian to be p squared by 2m plus half m omega squared x squared, where p and x, these are operator. So Hamiltonian operator in quantum harmonic oscillator, one dimensional, can be written like this. So we have to find the ground state and excited state, like we have to find the eigen value and eigen state for this Hamiltonian. So let us proceed. So before proceeding, we can do this by two ways. One is by brute force method, like we put this Hamiltonian in our Schrödinger equation, minus h cut square by 2m del 2 psi del x square plus v psi equal to h psi. So if we put our potential here and if psi is our eigenstate of Hamiltonian, then H psi can be written as E psi. So from here we can find the E and psi accordingly. So this is by brute force method, and another method we have, which is our ladder operator method. So here I will discuss this ladder operator method. So before proceeding, so suppose we have a classical harmonic oscillator Hamiltonian. So we have this one. So this is our classical harmonic oscillator Hamiltonian. Now we know that if we have two numbers, so if P and X in classical case, they are numbers. So we can write U square. So suppose we have squared of this two term. So we can write this as U plus IV into U minus IV. So how can we write this? So this will give us U squared. This one will give us V squared. And we have I UV minus VU. So U and V, if they are numbers, then this term will be 0. So this is equivalent to this only if U and V commutes. So that's where the problem come in case of a quantum harmonic oscillator. In quantum harmonic oscillator, P and X, they are not numbers, they are operators. So our operators doesn't commute in generally. So they doesn't commute in general. So we can't like this P squared by 2m plus half m omega squared x squared. If this P and X are operator, this is not same as P by root 2m plus half root over m omega x plus this will be I, and P by root 2m I by root 2, so this will be root 2 m omega x. So if this P and X are operator, these are not equivalent. So but with this motivation, we are defining two operators. One is raising operator and one is lowering operator. So why they are raising and lowering, that will be cleared in few minutes. So let us suppose this is our lowering operator. And we are defining this as 1 by root over 2 m h cut omega m omega x plus ip, and we are defining our raising operator. So this is our raising. So raising operator we are defining as 1 by root under 2 h cut m omega x minus ip. So if we have a raising and lowering operator, then now calculate a Dagger. So what will be its value? We have 1 over 2 h cut m omega, and here we have m omega x plus ip and m omega x minus ip. So what will we get? We will get, like, here will be m squared omega squared x squared plus we will have the last term to be p squared, and we have two more terms, which is minus I m omega x p minus p x. But we know that x p commutation is I h cut. So that means x p minus p x, this is equal to I h cut. So we will replace this value here. So what we will get? 1 by 2 h cut m omega m square omega square x squared plus p squared, and we have here I h cut, so we will get m omega h cut. So from here, if we observe this carefully, so we will get half plus 1 by h cut omega p squared by 2m, and we will have m omega x squared omega squared. So what is this? This we know is our Hamiltonian. So this is our simple harmonic oscillator Hamiltonian, quantum one. So we will replace this here. So we have half plus h by h cut omega. So we can write our Hamiltonian to be h cut omega a Dagger minus half. So this is our Hamiltonian in terms of raising and lowering operator. Now let us calculate the commutation between A and A Dagger. So we know the value of A and A Dagger. So it will be 2 h cut m omega. For A we have m omega x plus ip, and A Dagger we have m omega x minus ip. So the first term will be x commutation with x, which will be 0. Similarly, the last term will be p commutation with p, which will again be 0. So we have terms of this commutation with this and this commutation with this. So let us proceed. So we have 2 h cut m omega, and we have m omega here. So what will be the commutation of this and this? So we will have x minus ip. This is our first term, and we have another term which is ipx. So we can write this as 1 by 2 h cut, and from here we can have minus I, and we can have I here. So basically we will have product with 2i, and we have commutation of p with x. So we know xp commutation relation is I h cut. So px will give us minus I h cut. So from here we will get this commutation relation to be 1. So A Dagger minus A Dagger A, this is 1. So in the Hamiltonian we can write this A Dagger, we can replace this by 1 plus A Dagger A. So if we replace, we will have our Hamiltonian to be h cut omega A Dagger A plus half. So this is our Hamiltonian in terms of this raising and lowering operator, and this A Dagger A, this is our this is represented as number operator or n. So why this? It will be clear in a few minutes. So ultimately the Hamiltonian we have is n plus half. So we can write our quantum harmonic oscillator Hamiltonian, which is of this form. So we can write this, if we represent this in terms of raising and lowering operator, so then we will have our quantum harmonic oscillator Hamiltonian to be this. So okay, what now? So now we are making a big claim. So what the claim is? So claim is that if suppose our wave function is psi and it satisfies the Schrodinger equation with energy E. So it satisfies our Schrodinger equation with energy value E. So this is, we are assuming that we have an wave function which satisfies Schrödinger equation, and what is the eigenvalue for this state? In the energy eigenvalue is E. So that means we have Hamiltonian. If we act on state psi, it will give us E psi. So now we are claiming that if we operate a Dagger on psi, so this will be so this is an operator. So if it act on a state, so it will be a new state. So this new state, it will satisfy the Schrödinger equation with energy value E plus h cut omega. So this is our claim. So what the claim is? The claim is that psi is an eigenstate of Hamiltonian with eigenvalue E. Then a Dagger psi, it will also be eigenstate of the Hamiltonian but with energy value E plus h cut omega. So let us prove this. So for that we have to first calculate two commutation relation. So let us first calculate HA. So what will be its value? We know H is h cut omega a Dagger A plus half commutation with A. So in the second term we have a constant. So this commutation will give us 0. So we have only our first commutation relation, a Dagger A. So what will be its value? So we have h cut omega. We can write this as a Dagger A plus a Dagger A product with A. So this term will be 0. So we have a Dagger A commutation relation, which we know a Dagger is 1. So a Dagger A will be -1. So we will have h cut omega A. This is our first commutation relation. And similarly, if we calculate the commutation of H with a Dagger, we will have h cut omega a Dagger A with a Dagger. So similarly, we can see that h cut omega. So here the first term will be a Dagger a Dagger, and the second term will be a Dagger commutation with a Dagger, and we have A. So this is 0. So what we are left with? We are left with a Dagger, which is 1. So this will give us h cut omega a Dagger. So this is our two commutation relation. So now we are ready to prove this claim that a Dagger psi is a eigenstate of Hamiltonian with energy value E plus omega. So how we will prove this? We will operate H on a Dagger psi. So we have this operator H a Dagger. This operator is acting on psi, but we know that H a, this operator has the value h cut omega a Dagger. So from here we can write H a Dagger to be a Dagger H plus h cut omega a Dagger. So if we replace this by this, we will get a Dagger h psi first term, and second term will be h cut omega a Dagger psi. So what is h psi? H psi we know is E psi, because psi is already an eigenfunction of Hamiltonian. So this we can replace by E psi, and since E is a number or a constant number, we can take it outside. So we have E a Dagger psi plus h cut omega a Dagger psi. So we can write this as E plus h cut omega into a Dagger psi. So we are operating the Hamiltonian on the state a Dagger psi. So suppose we are giving this name phi. So if we operate Hamiltonian on phi, we are getting a value and we are getting the same state here. So this must be an eigenfunction of this operator with corresponding eigenvalue this. So we proved that a Dagger psi, this is an eigenfunction of Hamiltonian. And what is the eigenvalue? with eigenvalue E plus h cut omega. Similarly, we can see that if we operate this h on a psi and do the mathematics as described here, then we will get E minus h cut omega a psi. So a psi now is also an eigenfunction of the Hamiltonian with eigenvalue E minus h cut omega. So by acting the raising operator on state psi, we are increasing its energy value, and by acting the lowering operator on state psi, we are decreasing its energy value, and so that is why they are called this raising and lowering operator. And we also have this number operator. So we know that number operator commutation relation with a, so this n or number operator we know is a Dagger a, so it will give us as we have already calculated it before. Similarly by acting the number operator on a Dagger, we have already calculated it to be a Dagger. So this is our commutation relations. So with all this in mind, so now let us calculate what is the lowest possible energy of an harmonic oscillator. So how to find this lowest possible energy? We know that if we apply the lowering operator on a state with energy value E, then what will the lowering operator do? It will always reduce the energy of the system. So if the ground state wave function, suppose it is 0. So suppose this is our ground state wave function. So this wave function must satisfy this relation. So why this should be true? Because if we know that the ground state energy is the minimum energy, no energy value is possible below the ground state energy. So if we apply the lowering operator on a particular, suppose this is our ground state and we apply this on ground state, and suppose instead of getting 0, instead of this we are getting another state. So suppose this is alpha, we are getting alpha or beta something. So if the ground state wave function has energy E0, then this state will have some energy E0 minus h cut omega. But this is not true because this should be the minimum energy. So but this value is lower than this. So this can't be true. So that is why the ground state wave function, if we apply the lowering operator on ground state wave function, it must always give us 0. So now we can represent this A. This A we know is m omega x plus ip. So now we are trying to find the form of this ground state wave function. So what will be the form? So we have m omega x. So let us find this is position basis. So in position basis we know that p can be represented as h cut by I del x. So if we substitute this, we have h cut del x 0. So this should be true for our ground state wave function. So we will get 0 del x minus m omega by h cut x 0. So we have 1 by 0 del x. This will give us minus m omega x by h cut. So if we do the integration, then we will get this 0. So since this is in position basis, so let us denote this by psi 0 x. So what will be the psi 0? Psi 0 x will be our A. This is our integration constant, and we will have minus m omega x square by 2 h cut. So this is our ground state wave function of harmonic oscillator in position basis. So this is our wave function, and what will be the energy value for the ground state? So we want to calculate the eigenvalue of H on 0. So we know H can be written as H cut omega A dagger A plus half. So we will add this on 0. So A0. So we have already demonstrated that A0 must be 0. So we are left with H cut omega by 2. So this is our ground state energy of quantum harmonic oscillator. So now we can see that this is our ground state wave function with energy value this. So denote this by E0. Now if we apply a Dagger operator on 0, what we will get? We will get another state with energy value E0 plus H cut omega. So that value will be 3 by 2 H cut omega. Now again, if we operate this operator on this, we will get 5 by 2 H cut omega 2, and in this way we can get the spectrum of energy, like what are the possible values of energy from this raising and lowering operator. So ground state has energy H cut omega by 2, first excited state has this, next excited state has this. So in this way we can calculate the whole spectrum of energy with the value, just with the help of this raising and lowering operator. But in a rigorous mathematical calculation, we have to show what are the normalization factor, because we know that wave functions has to be normalized. So if we so this is our ground state wave function. So if we apply this A Dagger, so it will give us it will give us a new state with energy value 3 by 2 H cut omega. And but there is it is not necessary that this state will remain normalized. So we have to find a normalization constant when we add this operator, this A Dagger operator on any state. So how we will proceed? So what will be the first excited state? So suppose this is our ground state and we are applying this A Dagger on 0, and this is suppose our normalization constant. So multiplying this with this, we are getting, suppose our ground, we are getting first excited state which is normalized. So in this way we can say that n state we can represent it as A Dagger n 0, because every time we operate A Dagger on 0 state, it will take its the state from its current value to its next excited state value, and an is the corresponding normalization factor for that state. So we have to find the value of this an. So first of all, we already know that 0 state, we already assume that 0 state is normalized. So this is normalized. So for 1 to be normalized, we have to have 1 should be 0. So what we will get from here? We will get A1 square 0 A Dagger 0. So this should be 1, and if we do the calculation, we will get, so we have 0 here, and A Dagger, this can be written as A Dagger plus A Dagger A. So this we are only using our commutation relation which we have got previously. So this should be 1. So from here we can write A1 squared 0. This will give us 1. So 0 1 plus A Dagger A 0. So this should be 1, and what we will have? We will have A squared into 0 0, because A0 will give us 0. So we can see that if 0 state is normalized, A1 squared, so the first excited state is also normalized. So now let us calculate this for nth state, any general state n. So for any general state n, if this has to be normalized, we have to have this. So let us calculate the value. So we have an squared here, and we have 0, an, a dagger, n, which will act on 0 and 1. So what will be the value? So we have, let us do the calculation here first. So 0, we can write this as a, n minus 1, a dagger, n minus 1. So this will act on 0 and 1. So this we are getting. So now we can write 0, a n minus 1. This a dagger, we can write this as a commutation with a dagger plus a dagger a. And we already have a dagger n minus 1, which will act on 0. So okay, so there shouldn't be this term. So this will be 0. So we have a n squared. So we have 0, a n minus 1. So what is this? This is our number operator, and this is value 1. So a dagger, we have n minus 1, and it will act on 0. So this should be 1. So this is just you have to do the mathematics and you will get the desired value. So we have like this term. So n minus 1 by a star n minus 1, and we have here n plus 1 operator. And similarly, if this act on 0, what it will give? It will give us 1 by a n minus 1 n minus 1. So how we are writing this? We are writing this because we have already see that n can be written as this. So n minus 1, this can be written as a n minus 1, a dagger n minus 1 on 0. So we are replacing this 0 a n by this term and this term, so and its complex conjugate. So in this way we can get this relation. So from here we are getting a n squared divided by a n minus 1 squared, and here we have n minus 1, n plus 1, n is the number operator, and we have here n minus 1. So this should be 1. So we will have a n squared, a n minus 1 squared, and what will this term give us? So number operator on any state will give us that n value. So it will be n minus 1 value, and for the second term, this is our norm. Since this n minus 1, this is normalized, so n minus 1, this should be 1. So it will give us 1. And we are left with this relation. So we have a n squared to be, so a n minus 1 squared to be n a n squared. So this is the relation that we get. So in this way, by iterating, we can show that a n square, as we have already seen, a n square can be written as 1 by n minus 1 squared. And similarly, if we replace this n minus 1 by n minus 2, as we have done for n, we replace n by this n minus 1. So in the similar manner, we can replace this by n minus 2. So we will get 1 by n multiplied with n minus 1. Here we will have n minus 2 squared. So in the iterative process, if we do the calculation, we will left with 1 by n squared a 1 squared. But we already know, so if we choose all the coefficients to be real, so what we are left with? We are left with n to be, so what are our n value? So n value is a n, a dagger n and 0. So a n value we have 1 by root n. So since this is 1, so we can write n to be a dagger on 0. So this is our this is our nth eigenstate. So if we know the ground state, and if we apply this raising operator on the ground state, so we can get any excited state with its proper normalization factor. Now we can write if n plus 1 as 1 by n plus 1 factorial a dagger n plus 1 acting on 0. So this term, how we can write this? So we can write this as where a dagger n 0. We can easily write this, and this we have already calculated. So what is this value? This value is n factorial by n plus 1 factorial, and we have a dagger, and this will give us n. So what is a dagger n? A dagger n is root under n plus 1 factorial by n factorial multiplied with n plus 1. So this is simply n plus 1 into n plus 1. And similarly, we can show that a n will be root under n minus 1. So this is all the results which we need for doing any mathematics. So basically what we have learned in this, so basically we represent our Hamiltonian, our harmonic oscillator Hamiltonian in terms of this raising and lowering operator, and in terms of number operator. So, and we show that if psi is an eigenfunction of the Hamiltonian with energy value E, then a dagger psi will also be eigenfunction with energy E plus H psi, and a psi will be eigenfunction with energy value E minus H psi. Then with all this commutation relation and all that, we have calculated the ground state, and we find a way by which, if we know the ground state, we can construct any excited state from where? From this formula. That means with if we iteratively keep applying this raising operator, we can find all the eigenstates, and we already know the eigenvalues. So that is why we can span the whole energy spectrum. And so in this way, you don't what do you have done? We have not done any rigorous, we have not solved the Hamiltonian, the Schrödinger equation explicitly. We just take the help of two operators, raising operator and lowering operator, and with the help of these two operators, we have spanned the whole energy spectrum, and we have find a way to calculate to calculate any excited state wave function. The ground state wave function we have also calculated with the help of this lowering operator in position basis, and from that, if we keep applying this raising operator, we can calculate any excited state.